Okay, so this is the the third video and this video is on the hexadecimal system and text storage of different text characters. So where are we, right? So we've just spent quite a bit of time hopefully getting familiar with binary numbers. And from our last video, we know that computers speak, I guess we would say, or communicate in binary. And it is true that everything in a computer, whether it's data or actions, whatever, is stored or is processed in binary. So in thinking about data, in particular, anything that you know that's stored on a computer, temporarily or permanently, is just a bunch of zeros and ones, as crazy as that is to understand. So now, I guess maybe a reasonable question is, why, I guess, it certainly seems a little strange that the computer speaks a different language than we do. We obviously made computers, so why not sort of make them in our image, I guess. And there's a number of times and moments throughout the semester where we will, sort of pause and observe that there are a lot of similarities. In fact, I think in the first week's video, we talked a little bit about the CPU, the central processing unit, which in essence is sort of the analog of our brain. So there'll be some analogies between humans and computers, but this sort of numbering system, which is a pretty fundamental idea. I know that even if you don't think about numbers, they are in your everyday life. And matter of fact, if our world was binary instead of base 10, just think about it. Wherever you are right now, I'm sure sitting in your room or at your home or wherever you are, if you pick your head up for a minute and look around, I promise you probably find a base 10 number somewhere on a clock, on some other sort of display, somewhere, right? Probably on the device you're looking at, there might be a date showing what is the date right now. So our number system really is all around us. And imagine if we used binary. Well, that clock that you might be looking at that has a 9 on it for 9 o'clock wouldn't say 9. It would say 1001. I think that's the binary version of 9. So, it's sort of, as much as I know we don't necessarily think about numbers as being all that central, it is, right? It is an important part of our everyday life. So it kind of begs the question, well, why not make a computer's numbering system base 10, right? The way that we do things. So this in this chapter, we'll kind of try to think a little bit about sort of why binary, and we'll do that mainly by considering a different system to see if this actually maybe would make more sense or not. So what's the main benefit of binary is that since there are only two values, 0 and 1, it is actually extremely cheap, I guess is really the most important acknowledgement, and also simple, I guess, cheap and simple. And by that, I just mean that making a bit physically, which again, there are millions and billions of them in your computer, making a bit that's just a 0 or 1 switch is very simple. I don't have to get too crazy with lots of settings. Again, let's use our human analogy of a light switch, just a regular old on-off light switch, versus a dimmer switch. You're probably not an electrician, but you probably know that there's a lot more that goes into making a dimmer switch, which gives you many, many, many settings, options, as compared to an on-off switch, just a regular light switch, which, push comes to shove, you might even be able to create. But a dimmer, right, that's a lot harder to make just one of them. So you can imagine, right, if we were going to go some other system that wasn't binary, a computer, which might still be sort of small, and a cell phone, which is very small, wouldn't be made up of bits anymore. It would need to be made up of, well, whatever system we choose to use, it would need to be made up of a bunch of memory spots that are capable of storing however many digits we want. So binary, why did that sort of win out? Is because it was very simple and very cheap in order to make something, right? That just basically what you're just sort of envisioning is a little box in memory. And all this needs to be able to do is either have the number 0 or the number 1 in it, which is a pretty simple physical construction. If I've got to make something that can hold our number system, 0 through 10, or 0 through 9, I should say, I got 10 different settings. I can't just get away with sort of an on-off switch. I'd have to have, something more like a dial that has, 1, 0 through 9. And then data would be stored by sort of saying, oh, okay, if I need to store the number 4, I, move my dial to the 4 spot, right? It'd be almost more like a clock or like a locker combination or something. So that didn't prevail as the best technology because it's much more complicated to make something like this as compared to something like this. And what prevailed in the end is that the idea of making a lot of these, each one of them is very simple. And you can make a lot of them, which we know we're going to need lots of zeros and ones to store a video, for example, or something like that. That's actually pretty simple. So making a lot of them and actually even putting a lot of them in a small space like a SIM card in your phone, that actually isn't that hard. Or I'm sure it was for the people that did it, but that's not the issue. So making a more complicated numbering system wasn't really, and our number system, the base 10 system, is much more complicated, wasn't the way to go. Instead, the founders said, well, even though, take a number like 99, which in our world we can write with 2 digits, you need 7 bits to write that number, which we can say we can write in 2 digits. Wouldn't 7 somehow seem less efficient? So let's consider, right? Would there be other ways to do this, aside from our system, that maybe would be still at least equivalent, if not maybe a better way of representing numbers. So we present one other system, which I won't ruin the surprise. We'll just sort of move ahead. I'll tell you how this fits in with binary in a little while. So let's imagine not our number system. So 10, I mean, we use a base 10 number system literally because we have 10 fingers. That's it. There's no amazing story as to why we chose 10 or why whoever chose 10. It's because we have 10 fingers and 10 toes. So 10, let's skip that. Let's skip our numbering system for a minute and say, how about what would a base 16 numbering system look like? Well, for this, let's just follow our knowledge of the binary system, which we now know quite a bit about, and our number system, the base 10 system, and make some natural extensions. So our number system uses 10 digits. Binary system uses 2 digits. So a base 16, if this is our goal, would have to use 16 digits. In other words, or 16 numerals, you could say, or 16 symbols, characters, whatever you want to call them. And okay, so and then in a base 2 system, binary, we know the place values are powers of 2. So for a base 16 system, I guess the place value should be powers of 16 in order to, sort of complete this analogy. In binary, I multiply by 2, multiply by 2, multiply by 2. So for base 16, I should start with 1 and multiply by 16 and multiply by 16. Okay, and I have no idea what the next one is, but whatever that might be, multiply by 16. Okay, those are at least the ground rules for what a base 16 system would look like. And in fact, there is such a system. It's called hexadecimal. Hex means 6. You guys probably know a hexagon, right, has 6 sides, so hex means 6. And decimal, dec, means 10. So it's 6 plus 10, or 16, base 16. So if we're trying to write down this system, and this is this system called hexadecimal, How do we do this? So we've got the place value thing sorted out maybe, but I might immediately sort of acknowledge that I might have an issue with the first bullet here, which is that I need to have 16 digits, I guess, or 16 characters. Huh. Well, I mean, unless I'm weird, I'm probably going to use these characters. Of course, there's 10 of them. But in our world, if I try to say I need more than 10 characters or 10 digits, if I just use numbers, the next digit, of course, that I would write down would be 10. But 10 is not a new character, right? 10 is just a zero, a 1 in the tens place and a 0 in the ones place. So a 10, of course, is just made up of my original 10 digits. And in fact, as we know, all the rest of the numbers in my numbering system are just going to be made up of these first 10 digits. So I sort of run out of digits. If I need to get 16, where am I? 16 numerals or 16 characters to be in this language, this hexadecimal system, I need more characters. In fact, I need 6 more, right? So naturally, you might say, well, I don't know, where else do I know characters? Well, I used all the numerical characters, so maybe a reasonable thing to do might be to say, well, if you want to know what's after 9, maybe I should start using the alphabet. And indeed, that's exactly what we'll use. We'll use A, B, C, and then we'll also use D, E, F. So let me sort of jot these all down. So the characters we might use will be our 10 numerical characters, and then we'll use the first 6 letters of the alphabet to represent our 16, right? So in hexadecimal, these would be our 16 digits or 16 numerals or whatever you want to call these. Okay? Where 10 is represented, in our world, 10 is represented by A in hexadecimal. B represents our number 11. C is 12, D is 13, E is 14, and F is 15. Okay? So let's see this all coming together. So here we are. I recapped it here for us. So if we want to try to say, what would this hexadecimal, this base 16 numbering system look like? So here we've figured out our big mystery of how to have 16 symbols. We use all the letters, all the numbers, 0 through 9. That's 10 symbols. And then if we want the next 6, which we know in our world should represent numbers 10 through 15, let's use the first 6 letters of the alphabet, right? So you can see that here. A through F, which would represent, in our world, the numbers 10 through 15. Okay? And again, much like all of our other systems, right? This is a base 16 system, and so our characters, or our symbols, go from 0 to 1 less than 16. In our number system, which is base 10, our characters go from 0 to 9, and 9 is 1 less than 10. There's 10 of them. And of course, in the binary system that we've been looking at recently, we just use 2 characters, 0 and 1 is, of course, 1 less than 2. So this by analogy is the exact same idea of both base 2 and base 10. And like we said at the beginning, my place values should be powers of 16 now, not powers of 2 like they were in binary, or powers of 10 like they are in our world. But if it's base 16, powers of 16. Okay? So, for example, this number, which I know looks kind of funny, in hexadecimal, 2A3D, how much is that actually worth? Well, much like we've done with binary, we can do a little chart maybe to help us convert. So the place values for hexadecimal, I'll sort of do the problem down here below also, is I'd start with the ones place, but then it's base 16, so I multiply by 16 to get 16 in the second digit there. The third digit I multiply by 16 again, and I get 256. And the fourth digit I multiply by 16 again, and I get 4,096. So this number, 2A3D, is actually how much? Well, I'll use the same idea that we've used for binary to say, oh, well, the place values are here. I have them. I know how much each of these characters corresponds to. So I just do my usual sort of arithmetic at the end, where I might say this 2 that's in the front is actually two of these, right? So I might say that's 2 4096s. A, remember, A is in our world the number 10. So I have A 256s. Remember, A is 10. So I would say that I've got 10 256s. 3 is still the number 3, as much as this is a bizarre system. So I have 3 16s, so 3 times 16. And D is actually the equivalent to the number 13 in our world. So I have D, or 13, ones. So 13 times 1. And lo and behold, in our world, this number, 2A3D, is actually the number 10,819. Okay, so... okay, I guess that's really all I would say about this right now. This is cute, I guess. And sure, this is a system that we could have. So let's think about it a little bit and sort of analyze pros and cons. So on the one hand, in our world, this number, which we know what that is, that's 10,819, whatever we might have. That needs 5 digits, right? 5 base 10 digits. There, you can see them right there. So in hex, which is where we started this problem, it was 2A3D. So in hex, you can actually write it with fewer digits than in our world. And actually, if you compare it to the binary world, 10,819, this magic number we're working with, if you do like we did in the last chapter, if you write that in binary, you actually get that it's that, okay, whatever that number is, all those zeros and ones. And that's actually 14 zeros and ones. So to store that number, our number, 10,819, you'd need 14 bits of memory, and this is how you would store it. So far, at least in terms of numbers of symbols, I guess, or numbers of characters, we've got this number in base 10, 819, right? That's 5 characters, I guess. In hex, it's just 4 characters. And in binary, it's that whole thing. I guess I'll write it down. 101010111110, which is 14 characters. So just based on how, on the number of symbols, I mean, hex appears to be the winner, at least in terms of it being the briefest. And it is. There's no argument with that, right? It is the most concisely written, or most concise way of writing the quantity 10,819. This doesn't help us a whole lot as a human being if I say this used car costs $2A3D. I think you're probably gonna get punched in the face or something. It's not really a way that we communicate. But if we did, right, I don't know, if we had 16 fingers and 16 toes, we might be sort of living in a hex world. And in which case I would say you can communicate larger numbers with fewer digits, fewer characters in hex. So this seems to be one thing that hex definitely has going for it. So it seems, right, that hex might be more efficient. However, the fly in the ointment is that how do I store a hex digit? Well, a hex digit is something between 0 and F, right? That's my alphabet, so to speak, for hex numbers, is 0 through F, which means I need 16 options. Right? Remember our old picture of a bit. A bit is ready to store a 0 or a 1, and that's it. So I can't really store, I don't have 16 options in a bit. So I don't think I can store 2A3D. I can't store this in 4 bits. That's not correct. I can't say that. So how would I do this? And maybe a better question is, what the heck does a hex bit, or sort of the hex equivalent of a bit, look like? Well, I need 16 options. I need to code all the numbers 0 through 9, plus these first 6 letters that we're using as our numbering system. So I need 16 options. So if I was going to try to encode that somehow, I'd need either some sort of newfangled device in a computer that's got a dial or some other sort of setting that lets me go 0 through 9, and then A through F. And it'd have to, have some sort of a knob that you could set to be any of the 16 quantities. Okay, well, that's definitely not a bit. And in fact, just like we mentioned, or I mentioned at the beginning of the video, this would be very expensive to construct. And you'd still need millions of them to probably store, a photo. And it's definitely way more complicated to try to make a device like that. So if we were trying to say, you know what, let's not totally throw away this brilliant idea of a bit, which is just 0 or 1. Let's try to put these ideas together. So I say, all right, if I want to figure out how to store a hex digit, one of these 16 options of basically the numbers 0 through 15, the most natural thing I might do is to say, well, if I'm going to try to jam this into the structure of binary, I might just use the binary equivalent. So if you think about the numbers 0 through, remember, F is 15, I can write that, I think. I have the ability to write 0 through 15 using 4 bits. Remember the thing we learned about last week, right? That if you have n bits, you can write all the numbers 0 to 2n minus 1, okay, which is good enough for 2n different codes. So here I have 16. I need 16 different codes. I need 0 through 9 and A through F. That's 16 different codes. So in order to get 16 codes, I better use 4 bits, right? Because 2 to the 4 is 16. And that should enable me to do all the numbers, right? So if I use 4 bits, I should be able to do 0 through 2 to the 4th minus 1, which is 15. And that should be 16 codes. Okay, so I say to myself, all right, I'm going to use 4 bits to store a hex digit, and I might just use the hex equivalents of the numbers, since that seemingly probably makes sense. So how do I code the hex digit 0? I use the binary version of 0, which is 4 zeros, and so on. How do I code the number 3? I convert that to binary, and I say, oh, that's a 1 in the 1's digit and a 1 in the 2's digit. That makes 3. And so on and so on. And then when I get to my letters, A is the number 10, remember? And how do I store 10 with 4 bits? That's a 1 in the 8's and a 1 in the 2's. That makes 10. All the way up to F, which remember F is 15. And that would be 8 plus 4 plus 2 plus 1. That's 15. Okay, so I can naturally, I think, encode any hex character as exactly and uniquely as 4 bits. Okay, so if that's the case, then what am I really looking at here? So let's come back to our original question, right? I had this number in our world, 10,819. And it's true, I can express that or represent that in fewer hex digits. However, if I want to actually store this, each hex digit, as we just discussed, you need 4 bits. Oh, so to store 4 hex digits, like we were trying to do with this number, I would actually need 4 times 4, or 16, bits of memory. Oh, well, remember the binary version that I had on a few slides ago with just zeros and ones for 10,819 only needed 14 bits. Oh, so hex in some ways actually is even worse, or is even less memory efficient if we switch everything back to bits to try to speak and communicate in the language the computer speaks. I actually end up in some cases in worse situations. So, moral of story, right, is that it does sort of seem like binary is inefficient because you come up with these big, long expressions for numbers that we can write in a shorter format. However, it is actually the optimal choice, because any other choice that I might make, like this seemed like I was onto something. Look, just 4 digits. But how do I store those 4 digits? Well, if I still want to use binary, which is my very easy, cheap storage, I actually end up needing more storage than if I had just stuck with binary in the first place. All right? So for this and many other reasons, it really is the optimal choice. So why am I torturing you, I guess, and making you learn or think about hex? What is it actually used for is a good question. Well, there's a lot of compatibility, which maybe you hopefully are already seeing, between hex and binary. Now, it's true, binary is the winner. That's what your computer speaks. It doesn't speak hex. So what does hex, what role does hex actually play? Well, we just saw, right, that every hex digit can be expressed as 4 bits, 4 zeros and ones. And, okay, so how does that help us? Well, 16, right, which of course is the base of the hex system, is actually one of the place values in binary, if you remember, right? So 4 in binary, right? 16 is one of the place values, and so of course every power of 16, which is what hex is based on, is also a place value. And in fact, it's every 4 digits. I can draw a few more of these out for us here to look at. Okay, so the hex digits are the 1s, the 16s, the 256s, right? So every 4 digits, as you can see here, if it was binary, every 4 bits corresponds to a hex digit. So this is sort of a nice way, not so much of actually storing numbers. Hex is not really actually used to store numbers, but it is a nice shorthand, is probably the way to put this, of a nice way to very briefly and easily shorten a binary expression, especially when we're trying to communicate sort of with a human who can, understand more difficult concepts. So let's see it in action first, and then I'll call your attention to a moment in all of your lives where I promise you've actually seen hex in action. So let's just do a couple quick conversions here. So if I have the hex number A73, and I want to convert that to binary, an easy way to do that is just to say, okay, so I've got, let me sort of write it here, A73. Well, each hex digit we know corresponds to 4 bits, 4 binary digits. And in particular, the nice thing about hex is that since the place values are so compatible, you don't have to go through a big construction where I'd say, oh, let me convert this back to, I guess, base 10, and then to binary. You can actually just go directly back and forth between them just by considering how much each digit in the hex form would translate to in binary. So 3, for example, that I start with in the ones digit, how do I write 3 in binary? I think I write 3 in binary as 0011. That's 3. So how much does this 3 translate into? 0011. Okay, next I go to 7, and I say, how do I write 7 in binary? Well, 7 in binary, I think I can do 7 in binary should be, let's see, I think I want 1, 1, 1, 0. I think that should be 7. So the 7 that's here actually also just translates exactly like that, 0, 1, 1, 1. Okay, and then the A, remember A, our first digit is 10, and 10 in binary, if I think about 4 digits over here, 10 I think should be what? 8, 0, and then I want a 2, and then 0, right? That should be the number 10. So that's actually just what A translates into as well, 1, 0, 1, 0. So the beautiful thing about hex and binary is that it is just this easy to switch back and forth between them. And this number, which now has what, 12 bits? 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1. I promise is the same thing as the number A73 in hex. I don't know how much that is in our world, but I'm sure if you convert them both, you'd get the same thing. So, and that's pretty quick, right? That's pretty simple to be able to take, to go back and forth then between one and the other. So how about we just go the other way real quick here. So if I want to switch from binary to hex, and here's my binary number. Again, to write it as hex, I think the easiest thing to do is just to sort of consider each group of 4, and see what binary conversion to hex each of these 4 bits would correspond to. So let's see. So if I start with the first group here, 1, 0, 1, 1, 1, that's, remember, our coding system for binary here. 1, 0, 1, 1, let's see, so that's 8 plus 2 plus 1, which is 11, which in hex is the character B. So this translates into B. All right, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, that's just the number 2, which in hex is still 2. And then the first digit, or the first group there, 1, 1, 0, 0, 1, 1, 0, 0, is what, 8 plus 4? 8, 4. So that's 12, which in hex is C. So C. So this binary quantity, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, translates pretty easily just to C2B in hex. So it's the back and forth between these two that's actually much more, that's the payoff for why hex is nice. And it is, as you can hopefully see in front of you, it's just a shorthand way of expressing a binary number. So rather than having to write in our world, right, to try to sort of communicate with each other, if I want to describe this binary quantity, I could write it's C2B, which of course is easier to express, right? It's easier to write C2B than all of those 12 digits. And even though a computer only speaks binary, we can sort of, as a human, speak, well, whatever, sort of whatever language is the best for us at the time. So it's not true that hex is actually, sort of understood, I guess, or it's not true that there's any hex memory in a computer that's ready to store C's and E's and things like that. But as I said, it is easier to, as a convenient shorthand, especially in communicating between a computer and maybe a human. Because a human can say, oh, if there's a hex expression given to me, I could either translate it to binary if I want to know binary, or base 10 if I want to know how many that actually is. So what is the place where you've all, I think, seen hex? If you've had your computer crash, which we certainly all have, you might notice that sometimes your computer tries to tell you things like that there's errors, or it tries to give you some sort of message. And if it's trying to sort of describe where something is or where an error might be, if you've ever noticed it, it doesn't give you binary. It doesn't actually try to which is a little bit funny, right? I mean, the computer everything in a computer is binary, and yet it's sort of, the people who make computers are smart enough to know that spitting out a binary address for something or a binary expression, it takes up a lot of characters, right? So if I try to describe where an error is happening in binary, it's a huge number. It's a huge expression. So what does it say? And if you've ever had an error, you might notice you probably, prior to taking this class, just said, well, it's communicating in letters and numbers. And okay, sure it is. And for us, when we see numbers like 5 and 9, we don't think anything of it. Oh, the computer's telling me 5 and 9. But the letters, which maybe at the time you just assumed, well, maybe it's also using the 26 letters of the alphabet, are actually hex letters. And so if not that I'm encouraging any of you to break your computer right now, but the next time you get some sort of funky error where it's trying to tell you, and by you I really mean sort of someone who's trained to probably debug it, if it ever gives you a sort of crazy number as a reference, I bet you it's got letters in it, but I bet you the letters that are in it are just A through F. Because I think most of the time it's trying to tell you or communicate to you is a hexadecimal version of some binary quantity. So if there's an error in one of the memory registers or something, it might say an error at 5E9B. Rather than, that's, of course, each of those is 4 bits. So that would be 16 binary characters. So they could say error at, 0100, whatever that translates into. But of course, it's much faster for it to just tell you 5E9B. And then it knows, okay, if you're a technician, you're going to either convert that to binary and know where that is. So it's really just a shorthand way of kind of encapsulating, I guess, binary digits. And in particular, since each hex digit is 4 bits, remember a byte is 8 bits. A nice way also of thinking about this is that since a hex digit is 4 and a byte is 8, you could also have the nice compatibility that any byte of memory could be thought of as 2 hex characters or 2 hex digits. So anytime you have 8 bits, a shorthand way of saying, instead of 11001001, which is a mouthful, you just say C9, and it means the same thing. Okay, so just so we have a little bit of familiarity, I'll do these a couple of conversions. We've already done a few here, so let me move somewhat quickly through these. So let's try to maybe convert 2AD maybe to binary. That should be pretty easy. We saw how to do that already. But then maybe I should also see what it is in our world. And then how about I try to go from our world to hex? That might require a little craftiness. So let's do this first. Let's do 2AD first. So remember, I'm trying to say, all right, I'm thinking about maybe 4 bits. And I'm trying to say to myself, all right, 2AD. So 2AD. If I want to switch this to binary, all I have to do is convert the characters to their 4-bit equivalents. So D is the number 13. So how do I make 13 with bits? I would do an 8, a 4, no 2s, and a 1. I think that makes 13. So D converts to 1101. A is 10. And we've seen this already. 10, how do I do 10 with 4 bits? I think that's 1010. And how do I do 2? That one should be 0010. Okay, so this binary number is equivalent to 2AD. Again, it's very strange. This doesn't really work in our world, in base 10. I can't sort of say, we don't really use other bases, but I don't have this sort of natural conversion to be able to go back and forth. When we did binary to our world, we had a little bit of, we had to do some work in order to make that happen. But between binary and hex, super easy, super simple. Okay, but let's now do the conversion to decimal. So how much is 2AD in our world? So obviously you've got it in binary here, so you could convert from binary if you want. But let's go right back to 2AD and say, well, how much is that actually worth, right? How much is 2AD? So remember, we've got place values, which for hex are powers of 16. So 2AD, these characters land in these three place values. So D, which remember is 13, represents, right, so D, which is 13, represents 13 ones. A, which remember that's our number 10, represents the 16s digit. So that's actually 10 16s. And the 2 that's in the first place actually represents 256th place, I guess. So that's actually worth 2 times 256. Okay, so of course if I want to figure out how much all of this is, I could just punch this into a calculator pretty quickly. And I think if you do that, you hopefully maybe end up with 685. So that maybe is equivalent of our number, 685. Okay, so one more. So how about we do maybe the trickiest direction, I guess, or the trickiest conversion, which is to do our number 973, convert that to hex. Now again, one option you could do is convert it to binary, which you already know how to do, and then convert from binary to hex, which probably isn't that painful to do. But if we want to try to go directly from our world to hex, we could do that. So remember our strategy before with binary was to say, all right, if you've got a base 10 number, like 973, and you want to convert to binary, remember the idea that we did was we said, let me draw out blanks and see when I go past this number, because I know I won't need any more digits than that. So if I'm going to do this for hex, I'm going to write out my hex place values, 1, 16, 256. Now the next number is, I think, this 4084, I think. I don't remember the exact number. That's too much, right? I know I'm not going to need this digit because it's way more than the number that I'm working with. So at most, so I know I'm going to use, I can sort of chop that off and say, I don't need that. I can do this with 3 hex digits. And so, all right, now remember the story that I think I told you with binary was to say, pretend you have this much money, and then you just start from the left and go to the right and ask yourself, can I buy something that's priced at this much, this much, this much? Now with binary, you can only either do zeros and ones. In other words, you could either buy it or not buy it. With hex, remember, of course, I can use any number 0 through 15, right? So, or 0 through F, but F means 15. So it's not as much that I'm going to say, am I going to buy this or not? I'm going to say, how many do I want? Or how many can I afford, I guess is the question. All right? So I've got $973, and I'm going to start on the left, and I always want to buy as much as I can. So I come to the first item, and it's priced at $256. So I need to ask myself, how many of these can I afford? Which hopefully you can maybe just see the answer to that. But if you can't, take 973 and divide by 256, and you get 3 point something, which of course means you can afford 3, not 4, but you can afford 3 of those. So 3 256s would cost $768. So that's how much you are going to spend out of your wallet. And then I should probably subtract and figure out how much I have left, which would be $205. And so then I go to the next item. The next item is priced at $16, and I have $205. So of course I can buy some. And if I want to figure out how many I could buy, if I do 205 divided by 16, you get 12 point something. So I can afford 12 of these. So, I mean, you could write the number 12 to remind yourself that it's 12, I guess. But it's really actually not 12 as much as it's, remember, in hex, the quantity 12, or the number 12, is the letter C. So I might say, all right, I'm going to buy C, or 12, things that cost $16. So 12 things that cost $16 costs me $192. And that leaves me with $13. So I come to my last product on the shelf that costs $1, and I say, well, I got $13 left, so I probably can afford 13 of these. And 13, if you remember in hex, is D. So, and then if I spend my $13, of course, I'm broke. And so it must be the case that 973, our number 973, is apparently 3CD in hex. Okay, so that conversion isn't too bad. You can go in between to binary if you really want to, but yeah, I mean, I don't know. This isn't really. You still have to do this game where you sort of pretend you're shopping and buying stuff. So I don't know. This is probably just faster to go straight here than to stop off in binary in between. Okay, so, and I'll just make a comment, right? If you're trying to think about storage capacity, remember with binary, it was all about the powers of 2. If you had n bits, you could do 2n different combinations. So how about with hex? Well, with hex, everything is the same. It's just 16 replaces 2, since it's base 16. So if you have n hex digits, so n spaces, and you're going to do hex, I'll just write down a few of them here. Obviously, hopefully it's obvious, the smallest number you could write would just be to fill all zeros in, right? Which obviously would be the number 0. The biggest thing you could do, rather than putting zeros everywhere, I think, would be to put the biggest number we know, which in hex world is F, or the biggest digit we know, would be FFF. That's saying put 15, 15, 15 in the 3 spots, or however many you have, I should say. So if I fill my number with F's, that would get me 15 per slot, which is going to leave me 1 short of 16 to the n. Okay? So this is maybe, even just in our numerical example down here, right? How much is this worth, this whole, my FFF number here? Well, the first F is worth 15. Remember, all F is 15. So this 1 is worth 15. This F is, of course, worth 15 times 16. And this F is worth 15 times 256. So if I add these all up together, I promise you get 4,095. And what's the next place value? 4,096. And how much is that? That's 16 cubed. Sorry, that's 16 to the 3rd power. Okay, 16 cubed. Okay, so with 3 digits, you could make 16 cubed minus 1. So hopefully this makes sense that if you have n hex digits, you can make 16 to the n minus 1 as your biggest number. And again, in total, that's 0 through 16 to the n minus 1, which is 16 to the n different codes or different hex representations. Okay, so this doesn't probably come up very often because, again, hex is mostly a shorthand way of writing binary. So you're not really sort of computing stuff in hex a whole heck of a lot. But just for fun, since we're here, if you wanted to make 1,000,000 different codes, so every, banking codes or something like this, and you were going to give everyone a hex code, which is made up, of course, of, again, 0 through 9, with A through F also, how many hex digits would you need? Well, if I go about the same idea of saying, well, I can, with n hex digits, you can make 16 to the n different codes. Then how far do I need to go to get to 1,000,000? Well, if you just sort of do powers of 16, 16 to the 4th is about 65,000. So that won't get you enough to get to 1,000,000. But actually, if you go to the 5th power, 16 to the 5th power is just over 1,000,000, which means you should need 5 hex digits. And with 5 hex digits, you can actually make more than 1,000,000 different codes, which is kind of, I don't know, it's kind of impressive, right? In our world, if I have 5 digits, right, I can make all the numbers 0 through 99,999. That's only that's only 10,000 codes with 5 digits in our world. So in hex world, with 5 digits though, since you're using, in addition to using 0 through 9, you're also using A through F, with 5 hex digits, you can make over 1,000,000 codes, right? So you get a whole bunch more that come from the fact that you're using not just 0 through 9, but also 6 letters. So again, you do sort of see, in practice at least, how hex might be not a totally crazy idea. Of course, you start to get into the situation and say, well, maybe I should go even more than base 16. Why don't I go up to base 100 or something like that? Well, somebody thought of that, right? And in fact, the people who thought of that were people who, for example, made our language, or language in general. We don't just have 10 letters. We at least have 26 letters, right? And other alphabets are slightly different, maybe have more or fewer. So our alphabet is actually a base 26 system, in the sense, now, of course, our alphabet isn't numbers, it's letters, so it doesn't quite mean the same thing. But I have 26 different characters. So why doesn't a computer use base 26? Well, again, the idea is that it's a pain, right? It's difficult to learn all of these different characters. Can you imagine having, right, when we were kids, it took us long enough to learn the numbers. Learning the letters was actually harder because there's more of them. And if you were going to use some other base system like base 10 million, you'd have to have 10 million different characters. So of course the trade-off is that yes, you could express things more concisely, but it requires the person on the other end of the line, or a device on the other end of the line, to recognize 1,000,000 different characters. Well, that's super not optimal, right? So anyway, but this is sort of a nice little survey of different systems, right? Different numbering systems. All right, so where are we in the story? So we're moving along this list of trying to understand, when I say everything is binary, right? Okay, what exactly does that mean? Well, I think by now we've mastered numbers, right? So we now know all about numbers and storing numbers in binary. So what else, right? So it is true, right? I'm not kidding that everything is binary. So, well, let's go to the next group, which might be to say, well, how about characters or text or characters? How do I store those as binary? Well, when I think about text, I say, well, all right, what's different about this than numbers is that, well, there's more characters, right? There's more characters, just like I said a minute ago, right? Our alphabet has 26 characters. So how do I can't really use I can't just use numbers. I have to also say, well, how else could I maybe incorporate this? Well, binary just uses zeros and ones. So how do I get sort of beyond that? Well, hex, as we just saw, at least gets you all of the numbers plus some of the letters. But that's not enough either, because I got to get all the letters, not just A through F. So maybe I'm supposed to do something like base, what? I need 10 for the numbers, and I need, 26 for the letters? So I guess maybe I could do something that's base 36. But then I might say, well, that means I need an awful lot of characters. I need an awful lot of representations. Well, so what's a more reasonable thing is to ask ourselves maybe these basic questions. Well, what do we need representations, or what do we need symbols for? And that'll help us hopefully answer the question, if we're going to do binary, which of course we are, how many bits do I need, right? So I know it so far has seemed like this idea of saying, okay, you can do 2 to the n different codes with n bits, like who cares? Well, for the first time, we're going to actually see that being useful, is it'll help us answer our second question. How many bits do you need then to represent that many characters? A good question, which we'll spend some time thinking about, is do you need to use the same number of bits for every character or for every symbol? Okay, I'll present a good example to demonstrate that. And okay, how does someone else sort of decode what these symbols represent, right? So how is someone else going to understand when I write 0100110 that that's the letter K, right? How is somebody going to know that? So these are some good questions that we want to ask and answer. All right, so easy thing first. What needs to be encoded? Well, I got to think about basically anything that you might type, anything that's on the keyboard needs to have a code, right? So when I hit the P key on a keyboard, I need a code. I need the computer to understand, oh, that's the P key versus the S key versus the 1 key, and so on and so on. So I certainly need to get all the keys, which is obviously all the letters, but I also need codes for lowercase and uppercase versions because they're different. So the computer has to know, oh, that's capital K versus a lowercase k. I also, of course, need all of the punctuation marks, including ones that are with shifts. Obviously, I need the numbers. And in fact, write any character or any key that I might hit, I need a code for, even the function keys or whatever you might have. I certainly need codes for all of those things. So how many things is that is a good question. And for our alphabet and for our system, it's not that crazy. But we'd also need codes for any other alphabet. So the Chinese alphabet, for example, is totally different. So how do we get a handle on how many codes we really need? Well, for our alphabet and for our system, there's approximately 220 symbols that we need to be able to have codes for. Again, think about the keyboard. I didn't prepare by counting up how many keys are on the keyboard, but it's all the numbers and all the letters. That's 36. Plus a whole bunch of other keys, right? So I don't know, maybe about 50 keys. And you also need shifts and maybe also control, right? So shift and 4 is the $sign, but control and V, for example, is a shortcut for pasting. So you need combinations of these things in addition. So we need about 220, as it turns out, different symbols to have codes. So we say, okay, 220. Let's see. I'm back to binary, so we're not in hex world anymore. We're in binary world. So I say, all right. Well, how many bits do I need for 220 different codes? So I ask myself the question. I say, I know that with n bits, you get 2 to the n codes. So if I run through and ask myself, so how many do I need? 8 it turns out is the number of bits that you would need in order to get 256 codes. Right? 7 bits, I think, would just give you 128 codes, and that's not enough. Right? So I need to go up to 8, and it just so happens, of course, that 8 bits is a byte. So in fact, each character, is going to be encoded with a byte of memory. Okay, so the next question is, do I need to have the same number of bits for every symbol? So, and I know here, so we're sort of trying to pretend like we're the creators of this code for all the characters. So we sort of have infinity flexibility to kind of do whatever we want. So, all right, we know we're going to use 8 bits, and we know we're going to try to come up with symbols for all the characters on the keyboard. So, all right, well, if I was to come up with systems, I don't know, unless I was a weird person, for the letters, I might just sort of start numbering them. And in fact, that's what the system eventually is going to look like. I'll show it to you in a little bit. So But let's see, how careful do I have to be about this? What if I'm trying to say, forget about binary for a minute, and just say, if I'm trying to come up with a system of encoding our alphabet, let's just worry about the alphabet for now, worry about all the other characters later. I might just sort of enumerate the letters. So in that sense, A might be 0, and B might be 1, and C is 2, and so on. But consider these two systems of, systems, I guess I would say, of writing the letters. The first system says, all right, start at 0, and then 1, and 2, and so on. And so does the second system. But the biggest difference that you see there is that the second system is going to always use two characters to represent each letter. So while it seems a little silly to do so, it's going to say A is 00, B is 01, C is 02, and so on. Okay? So a question is, which system is better? A or B, or first system or second system? Well, let's think about encoding the word can, C-A-N. How would this be encoded in each of our two systems? Well, in the first system, the letter C is 2, so I'd say 2 for C. The letter A is 0, so 0. And the letter N, I counted it out for you, is the number 13. Okay. Now in our second system, can, C-A-N, would be similar, but somewhat different, right? The letter C would be 02. The letter A would be 00. And the letter N is still 13, or 13. Okay, so in terms of what's better, well, on the one hand, shorter is better, right? Being as brief as possible, less memory, things like that. The first system uses fewer digits, especially for the C and the A. And so it would require less memory, that's true. So does this make it better? Well, I think we might see in the example that we're going to look at that the punchline is actually going to be that while it's appealing to try to sort of be as brief as possible, we really do need to use the same number of digits, or bits as it's going to be for us, for every symbol, because otherwise decoding these characters correctly is going to be impossible. So what do I mean by that? So let's look at this example. So this is a very good question. I'll ask you to probably explain some of this to me. So if I think about, again, our two systems here, one which doesn't use 2 digits every time, the first one, and the second system which does use 2 digits every time, then let's say someone, sends me the message or sends me the word 0110. Now, if I'm using the first system, this first idea, and I try to decode this and say, well, what letters does this correspond to? I might say, well, let's see, 0110. Well, 0 is A, and B is 1. Okay, so this is A, B, B, A. Sure. However, what if somebody else looking at the same exact code decided that it was a 0 for A? Okay, that's true. But what if somebody read that as 11 rather than 1, 1? Or rather than a 1 and then a 1. They read it as 11. They might say, oh, well, what's the 11th letter of the alphabet? Which is L. And then they might say, okay, so that 0 then is A. So that's the word ALA. Uh-oh. Well, even worse, just for effect, somebody else might look at this code in the first system of numbering and say, okay, that that 0 is A, that 1 is B, because it is, right? B is 1. And then that is the number 10, which 10 is the 10th letter of the alphabet is K. All right, so I'm going to go ahead and call this a problem because I encoded it, my message or my word, as 0110. And yet 3 different people could decode the same exact message, 0110, as 3 different words. In fact, even worse, these 2 words only have 3 letters, and this one has 4, right? So, okay, there's no way, right, that I should have this much flexibility in terms of decoding, because of course, what is the most famous thing we know of that's always encoded? Things like passwords. I wouldn't want to type in my password and have it encoded and then say, oh, the computer encoded my password as ALA because 0110 it thought was ALA. So when I go to log in and I type in ABBA, it's going to be like, that's not your password. And you'll be like, wait a minute. But it is, right? Oh, okay. Well, there's translation issues here. And we don't want uncertainty in decoding these symbols. So how about in the other system, right? So forget about this. Let me do this in blue now, and go to this system, right? Which was sort of second proposed one, which at its onset looked like it was maybe worse in the sense that it's a little wasteful, right? It does hurt us. It hurts our eyes a little bit to probably write 00. It's like you don't need 2 of them. You just write 0. But that led to a bit of a disaster up here, right? That this is not good. But if I was using the second system and I sent the number 0110, I think everybody will decode this exactly the same, because embedded in the system is the idea that every letter gets 2 digits. So when I look at this, I don't have confusion about, oh, maybe that's 4 digits. 4 letters, or maybe it's 3 letters. Maybe it's one of these 2 guys. Maybe 2 of these are grouped together and some of them aren't. No. In my blue system, my second system down here, everybody gets 2 digits. So I know those guys go together and those guys go together, and then it's just a matter of looking it up. And I say, oh, okay, 01, that's my code for B, and 10 is my code, the 10th letter of the alphabet, which would be K. So I was really sending the message BK, and nobody else in the second system could hopefully, unless you're wrong, you'd all write down BK. There's no other way to define it, because again, I make sure that I use the same number of digits for every character. Okay, so the answer to our lead-in question, do we need to use the same number of bits? The answer is yes, I do. All right. So with that in mind, what is our system? Well, there had to be a standard conversion, right? Again, I realize what I wrote on the last slide for our system was probably not going to quite cut it, and it wasn't even in binary. So, so great minds sat down and tried to figure out, all right, what are the symbols we need codes for? And what should those codes be? And there was at least some rhyme or reason to how they did this. And what is the coding system that we use? It's called ASCII, which maybe is something you've heard of. That's how it's pronounced, at least, which stands for American Standard Code for Information Exchange, which sounds very fancy. It's just a way of saying, how is my keyboard? How are all the things in my keyboard encoded? All right. So what are these codes? First of all, it includes, like I said before, anything from the keyboard. And it does use 1 byte, right, or 8 bits. So there's 256 codes. All right. So what are the codes? Well, this is probably not the most exciting chart to look at, but this is at least partial listing of the ASCII codes. So just a couple things to notice about this. Obviously, you don't have to know these codes by any means, but there is some rhyme or reason. So first of all, let's look at the numbers. Now, you might have expected, and I don't have a cute story for you as to why, you might have expected the 0 through 9 numbers, which we know have binary representations, to just be those binary representations. And you might say, well, they aren't, right? That this is not the number 0. The number 0 would be 0, 0, 0, 0, 0, 0, 0, 0, right? But a smart observer might say, oh, well, maybe that is actually still there. In fact, if you look at this for just a second, these are the numbers, aren't they? Right? If I just pull off the last 4 digits, that's the number 0. That's the number for 1. That's the number for 2, for 3, for 4, and so on. Okay? So now what is the number that's, and what's the number that's in front? Well, they're all the same, right? That's 0011. So what does that mean, or what does that represent? Well, that's the sort of lead code to say these are numbers and not somebody else. So if you see 0011, to interpret that, it's saying numbers, and then it's saying start at the number 0, and then that's the number 1, 2, 3, and so on. You'll notice a similar thing about the letters, is that the letters also of the alphabet go in order. If I do a similar sort of split, okay, the letters all have the same lead. At least these do, I should say. There's one other lead that you need for the rest of the alphabet. And then the numbers are in order. This is 1, this is the number 2, this is the number 3, this is the number 4, and so on. So it's all still there, right? And of course, it makes sense, hopefully also, that the lowercase versions of each letter are the same ending bits, right? So sorry, this is all messy. Let me give myself a clean slate here. So one other thing you might notice, right, is that the last 4 bits are the same for the cap and lowercase version, right? So lowercase g ends in 0111, capital G ends in 0111, and the only difference is what the first 4 bits are. So there is order here, and there is organization, as you might imagine. And, there should at least be some way of indicating some logic. Now, obviously, at some point, you sort of stop stop numbers and go into letters and go from letters to punctuation and all this other stuff. So the full ASCII table, of course, has over 200 symbols encoded. Again, anything on the keyboard has a code. And the good news is that this is the sort of agreed to system. So when you buy a computer, your computer knows the letter A, the letter capital A, for example, is the binary equivalent of 0100000001. And so does any other computer. So this is why it makes it possible to, be maybe talking with someone on some sort of messaging service, maybe, or maybe Skyping with someone and typing text. You're all using the same system. You're all using ASCII, no matter what kind of computer you're using or where that computer might be. All right, so that should wrap it up with, so we know by now how to do numbers in binary. We now know how to do characters, or I don't know, I never know exactly what to call these, but characters or text things, right? So numbers, letters, other things from the keyboard. So what's next? We sort of mastered all of the sort of one-dimensional easy things. So next is, how about images or pictures? And how about sound, right? So these are, let's be honest, there's a pretty big difference between just storing numbers and letters and storing something like a picture or an audio file. But believe it or not, it is a similar sort of idea, and it's a similar sort of process where we sort of say, well, how might I do this? Okay, how many codes do I need? And things like that. So next time, pictures and sound.